Hello, my name is Riku Voipio, and I work at Linaro in a so-called builds and baselines team. We build the images and run various tests on them that the kernel developers have created as kernels to test, and the QA will test them, but we build the binaries in the between. So in this talk, we will be discussing Lava, which we use for our kernel testing, and Git bisect, which is a tool that enables people to find where exactly the problems happen, which commit was the thing that broke things down. Here we have an imaginary case that somehow it has passed the testing that the time doesn't work anymore. It's in 1970. The last release, it worked. Now we need to find out what exactly caused the problem. Git bisect is a tool in Git. How many here have used Git bisect? So almost everyone. If you haven't, you should really. Well, the manual part of Git bisect is rather simple. You tell which the commit was where it broke, which is usually head, because you are just debugging it, and then some commit where still things used to work. The Git bisect algorithm will then start crunching the commits between to find which exact commit is broken. It's quite similar to binary search, so the amount of tests you need to do to get down to the bug doesn't grow that much, even if the commits get doubled. So each time you run git bisect start, it will give you a starting commit, you build it, you test it, and then tell if it worked or not. Git bisect bad for broken commit, and git bisect good for success. And in this small graph, we don't have that many commits to search, so it took us 4 steps to find exactly which commit was the one that broke us down. But if you have thousands of commits to search and less time to work on, you would probably prefer something automated. Git bisect run is an advanced mode of this git bisect, which will run a script, and depending on the exit code of the script, it will decide if it was good or bad. How many here have used git bisect run? A lot less, but some people have. So instead of sitting by your computer and running the make and test, you just run the script to do the tests and go do something else during it. In this simplified example, we have the bisecting script, which is a kernel build. We do a def config, and then we build the kernel and the DTB files for the OMAP platform. The exit code 125 is a magic value documented in the Git manual page, which means that skip this one. In our case, if the kernel build fails, we will simply ignore it, that it's a problem unrelated to the one we are searching right now. And the last line of the bisect script is my lava boot script that will boot the BeagleBone Black and run a test script, which was there in the first slide, test the hardware clock, and if it returns successfully, the time was correct, it will give a 0 exit code and something else if it breaks down. I had prepared a demo hardware here, including a power unit and a BeagleBone, but unfortunately, I can't set it up running right now as expected, so I have a pre-recorded demo as caution. We have the same test scripts here that were on the slide. slightly more verbose because we are being more specific, and we started with Ccache because we don't want to wait as long. So the first step is starting here. And the script runs for a while in an accelerated time frame. It will report the git commit ID it's testing, compile the kernel, and come out with the Lava job. The script has now uploaded the kernel and the DTB and started the job on the Lava server that is running locally. Now we'll return back to the slides while we wait for finish. So, Lava is the tool that Linaro uses for pretty much all testing we have. There are some cases where people like to do their own stuff, but we try to make Lava useful for everyone inside Lava. It could be said it's a meta-as service, now that everything should be reported, designed as service. It converts the developer boards we have into something that are available in web by few clicks. In Lava, we submit jobs for a device type and get down back the results. At the minimum, Lava requires serial access. It's like was said in an earlier talk that serial port is the most powerful thing in the embedded world, and if you don't have it on your board, go somewhere else. Network is very useful. It's possible to use Lava without it, but not really convenient. Power control, any kind of automation of kernel development, you have to have it. In the most manual case, you will just have a script that says, please go and reboot the board, but it's not really automation then. Lava has a command line interface and a web interface, and it's available in Debian with just apt-get install Lava. The demo case in this Lava laptop, this laptop has Lava server installed inside a KVM virtual machine, and we bridge over the KVM to the Ethernet interface, so all the NFS and TFTP services are easily available. And for power control, there's a small USB boxed relay here. The web interface is live, and currently it's idle because the demo we are running is a pre-recorded one. You can see all the previous jobs down here. Status of the devices and so on. The convenience of having it all running inside a KVM means that when I'm usually using it at home, I can have it in a server, and when I'm traveling, I can pick it up and just copy the virtual machine over to the laptop. Lava has a bunch of components that are separated and include some kind of separation, that it's not all one big bunch of code. We submit the job either using a command line tool or by the web interface. The Lava server process listens to XML RPC as well as just the normal web interface, and will check that the job is okay. And if it is, it will be submitted to the Lava dispatcher, which will actually do the running of the job. One Lava dispatcher is the main core process of taking care of the testing. In this, we had a graph. It talks about master images. We don't need that one since we boot from just TFTP and NFS. It greatly simplifies the use of Lava if you just keep a very small use case of it. Finally, the results are submitted back. To control power on Lava, there are several options. You can have an enterprisey PDU switch from eBay from about 100 euros. The new ones cost a lot more since the simplest and cheapest models are no longer available. You can have some kind of home automation system like the Ubiquiti mPower. It looks like a power socket, but it also has an Ethernet place you can connect and with HTTP switch individual ports on and off. Then going down towards the Qt embedded relay, we have the boxed relays, which just need a little bit of wiring to get them to work. And finally, all the way down the hill to the nonsense area is doing the relay and putting it to a Raspberry Pi. It will just take not much more than 10 euros for the components if you have some kind of board that has GPIOs already. Finally, for future, at Linaro, we are creating an OpenTAC device. It's a BeagleBone cape that will have power, Ethernet, serial lines, and more. It's tailored for Lava use, and it combines a lot of the wiring you see here if you come to look at the desk after the talk. Lava tool is the official command line interface for Lava. It talks the XML RPC to Lava web server, and it's asynchronous, so you just give it a job and it will return back. I've been actually told that it's not completely true and there exists some way to make it synchronous. So finally, the problem for automation or automatic scripts is that it reads authentication token from GNOME keyring, and it means that you may have to type in the keyring password every now and then. So it should work in GNOME, but for example, in some other desktop environments, which I use, it doesn't work. So I had to do something else to make this bisecting possible. So I wrote the Lava boot script, which is not a complete replacement of Lava tool. It just takes care of the use cases I care of. It's synchronous, so it starts the job, polls the server as long as the job runs, and then returns when it's finished. It starts a small HTTP server for the Lava to get its kernel and DTB for the target device. And it has some convenience features like substituting variables so you don't have to edit the Lava definition file for small changes of jobs. And finally, it stores the authentication token in a configuration file, which is slightly less insecure than having it in GNOME keyring. So the Lava boot interactions with the Lava server look a bit like this. We start by sending the kernel and boot artifacts to the proxy process, and then tell the Lava dispatcher via job control that please start the job. The Lava dispatcher will then pull the kernel and other boot artifacts and provide them over NFS and TFTP to the BeagleBone target. Then it opens the serial line and it becomes essentially a glorified expect script and runs all the commands you want on the BeagleBone target. Finally, as a shortcut, I just return the exit code back to the proxy process instead of via Lava dispatcher. A more clean setup would be to just read the values of the test results from the Lava results bundle, but it turned out to be untrivial, and I'd run out of time to do it, so I had to make a shortcut. So this authentication token I've been talking about is the key to automate Lava. It's a bit like the Amazon authentication token if you've been using the Amazon Web Services. You need to log into the Lava web server, create a new authentication token, and then copy-paste it from the web interface down to a configuration file. The configuration file used by the Lava boot is rather simple. You just tell what is the HTTP address of the web server, what is the end user account token, and the proxy as seen as from the Lava dispatcher. And finally, the only mandatory option still left is if it's HTTP or HTTPS. The Lava job definition used by Lava boot is in YAML, so you can also use JSON, but YAML is a lot shorter. So you just define the Lava command deploy Linaro kernel, which is the one that finds the kernel, device tree, and NFS root file system. We have the boot command, in which we just use the standard settings as defined in the Lava device configuration. You could also have your own script to run on uboot or many other variables you can give to boot Linaro image, but in this case we don't need to give anything. Finally, we have the test definition down there, which is being pulled from the proxy. The test definition will include the RTC test script. And of course, you need to tell Lava what is the actual device type you want to test on. So after the variables have been substituted by the script, it looks a bit more like this. It will take the proxy from the configuration file and the device tree, image type, and so on from the target specific configurations. In the end, we have this test definition YAML, which is a file included in the script, so you don't have to really care about it, which will just call the script that we gave on the command line. So if we go back to the end of the demo, we have found after a bunch of rounds that there is a specific Git commit that has broken down the setup. Okay, someone decided that we don't need clock support anymore, and no one actually tested it completely. In this test case, it took us 22 minutes to find out the actual bug, and it was something like 8 or 9 steps we had to do to compile and boot the kernel, 7 steps. So bisecting is rather useful and convenient, but it's also not without issues. First, the kernel should work for pretty much, or whatever software you're testing, it should generally work for every single commit. And if you have a sloppy work culture, it means that perhaps every second commit works. Someone does one commit which is partial, and then in the next commit fixes it. These kind of Git trees are not really bisectable because it will find a lot of broken commits in between. So in the cases of kernel, you would need to test every single boot that every single commit that it actually boots. Then you have something that you can test for more complex test cases. Also, if your Git tree has big merges, commits that touch random files all around. The result is that Git bisecting is not going to be simple. You may need to increase the range of commits you search. So even though the commit appeared from your point of view between, say, 2.6.16 kernel and 2.6.17 kernel, you may have to try between 2.6.14 and 2.6.17 because some of the commits come from merges that are from a lot longer time. We have to remember that Git is not linear history, but something more like a directed acyclic graph. So it's not just a binary search you do when you do a big Git bisect. This is just good software engineering practice when you use Git. Make sure that commits are relevant only to one thing. If you have a topic branch, make it sure the topic branch gets merged upstream as soon as possible instead of living for a long time. And this will help you in many other ways than just helping bisecting. Finally, if the bug is reproducible only randomly, then bisecting will give you completely wrong results. So you have to actually test that the bug is consistently reproducible. So I have some references here. There's the Enjoy Fighting Regressions with Git bisect slides that I really recommend for anyone to read who hasn't been using Git bisect. It will give you a clear explanations of why it's possible. And the rest of the are just manual pages and Lava documentations. Slides are online already, and I don't think I updated since the last upload there, so they are even up to date. So, any questions? Okay.
How easy is it to combine Lava with other QA solutions?
So it was asked how easy it is to combine Lava with other QA solutions. In its current format, not very easy, but the Python code base should technically make it possible to use other QA solutions as well. The problem is that usually every QA solution is complete, so it does everything from the web reporting to running the tests, and it's hard to take just one piece from one QA system and another one from another one. So there's been discussions about using at least Autotest together with the Lava, and there's something that could be used there. Okay.
So in following that question, for example, we use build.bot a lot. How does it play with build.bot to build the images and then test it afterwards with Lava?
So it was asked how would Lava play together with build.bot, and would it be run after the build.bot build? Yes, that's exactly how Lava would be used together with build.bot. We use Jenkins in this way in Linaro, so we run the compiles in Jenkins, and Jenkins will then call a Lava script to run the actual tests on Lava. Okay.
Why is having an Ethernet on the board a requirement for Lava?
Why is Ethernet a requirement, it was asked. Well, in its current form, Lava will communicate the test results, and it will download the test cases over network to the target device, run the tests, and return them back over network. It's somewhat possible to use without network. Then you would have to have a way to install an image on the device via fastboot or something, and this is not as convenient there's some fast boot support in Lava, but I'm not sure if it's completely possible to use without networking.
What about the USB or some more standard interfaces that you basically find on some other development that's not necessarily being needed?
So basically you're asking if it would be possible to use USB or some other method. I don't see why it would be impossible, but nobody has written the code for Lava for that.
We support Nexus devices.
So Vishal, what were you
We
saying?
support Nexus devices. At least it's possible for Android.
So we use Nexus devices with Lava without network, or?
Yes.
Okay, so it is possible.
I mean, it's convenient to use the Ethernet for the development board, but when you want to run the real tests on a real device, the device would probably not have
And that's true. So, but as Vishal just said, it is actually possible, and I just didn't know about this side of Lava. That there, I guess it's using fastboot and
Yes,
ADP.
to download the images and ADP to run the test.
Okay, so this is possible, but it's slightly Android specific right now. Okay.
What kind of user space are you running? I saw that you built the kernel, and what's about user space?
So we had in this case I was using an Debian-based root file system that was exported over NFS. There's a slightly confusing target type which is saying Ubuntu, which means Ubuntu or Debian's type anything with an apt get. It's also possible to use Open Embedded or other systems. There are some command line commands that it requires, like wget, or I think Python was needed for that Lava test shell, but you don't have to use the Lava test shell. There's also the option of, instead of having a NFS rootfs, to have an init-rd and run the tests there. That's even simpler and faster in some cases if you don't have you have a working network in the Linux, but you have working network in the bootloader.
How easy or how hard would it be to add, I mean, not from Linaro, but from ourselves, to add that support for a new device type?
It was asked how easy would it be to add a new device type if you are not from Linaro, and it's actually quite easy. You just take an existing configuration and replace what are the commands you would type in the bootloader, which are the same ones for your target device. So we have U-boot and UEFI support, and those ones you would probably not need to change much lines. If you have a more exotic bootloader, then you might have to do some more complex configuration. Yep.
How big are the user space requirements? I'm thinking about using this on OpenWRT with a system with 32 megabytes of RAM. So I assume there would be, for a bare metal system, about 10 megabytes available for the test wrapper or something like this.
I'm sure it would fit there,
Okay.
especially since if OpenWRT has network, so you can have an NFS where you could install the extra stuff if it run out of space.
Random access memory, not about the flash.
Yeah,
So I don't need Python or something like this on the.
that was the Lava test shell, which is an advanced tool to return results into the web interface, and it's somewhat optional, so you can skip that part. Okay.
I really like the concept of metal as a service. We just talked about devices with operating system. What about devices like microcontrollers or FPGAs without operating system?
So it was asked, what about microcontrollers and other smaller devices that don't have an operating system? I think it's currently outside the scope of Lava. Other things outside the scope of Lava is also bootloader testing. So you could only, it's been discussed how it would be possible to test bootloaders safely without pricking devices, but in most cases it's not easy. Okay.
So is there currently a backend for subversion for Lava? So you would normally use Git to do the bisect, but yeah, with our company it would be yeah.
So
You would need subversion support to use this.
So it was asked if there is a subversion support for bisect, and the answer, as I believe, is no. So Git bisect is a very Git specific feature and almost a reason on its own to switch to Git. Any other question? There was one.
Does it include, I mean, the focus of the Lava environment, is it only for the Windows kernel or Android as well?
It was asked what is the focus of the Linux kernel, if it's just the kernel, and what is the focus of Lava testing, just the kernel, or the kernel testing is the simplest thing you can do with Lava, but you can also test a lot of stuff in the user space side. We run LTP tests to validate a lot of the code, and we might run benchmarks to test that things don't regress, and so on. So after Lava has booted the system, you're pretty much free to run any kind of scripts for any testing. Okay, thanks to everyone for coming.